Okay, good morning, everyone. Thank you for joining. Today we have a talk by Dr. Mark Chung. Mark is a senior staff physicist at Lockheed Martin Solar and Astrophysics Lab. He's a PI for SDO-AIA starting 2016. He did his doctorate at the University of Göttingen and at the Max Planck Institute for Solar System Research before joining the current location. His work focuses on combining observations and numerical simulations to understand solar magnetic activity. In 2017, he received very prestigious Karen Harvey Prize for the AAS Solar from the AAS Solar Physics Division. And today we have a presentation entitled Testing the Physics of Solar and Stellar Flares with NASA's Solar Dynamics Observatory and radiative MHD simulation. So please, Mark, go ahead. You have roughly 45 minutes.
Okay, thank you, Gregory. And thanks everyone for joining this webinar. I hope you can hear me clearly. I've been told that generally the questions will wait until the end. But Gregory, if I'm going too fast, then let me know.
Yeah, sure. Go ahead. Yeah.
Yes. So I would like to start off by posing some of the broad science questions that at least I'm interested in, and I think many people who study flares are interested in. These are not all the questions about flares, but they are nevertheless some of the very important ones. So for example, we are interested in what are the physical mechanisms that drive the buildup of magnetic energy in the solar corona that eventually powers the flares and eruptions. But we also want to know what channels the abrupt release of this energy into other forms. So if the energy is magnetic energy in the corona, how is it that ultimately we see the commonly observed observational signatures, e.g. the X-rays and the EUV fluxes that increase by orders of magnitude? Now, we also want to know, given that we have EUV and X-ray observations, what do we learn about the temperature and perhaps the magnetic structure of the corona, of the plasma in the corona? Of course, we can use other measurements like radio, like UV, like visible to study other aspects of flares. I won't go into that too much at this stage in this talk. I'll also talk about, given that we learned something about solar flares, what can we learn and apply? How do we apply these lessons to stellar flares? Now, this talk will not cover particle acceleration, so if you're interested in that topic, I apologize. I won't say too much about it, but nevertheless, I will talk about whether it is absolutely necessary to explain some of the diagnostics that we commonly use that we associate with particle acceleration. So let's look at some movies of SDO-AIA. For instance, this is in a few channels of AIA where there is a flux rope that seems to erupt and leave behind a flare. But in AIA, we also see that when comets go through the solar corona, like here, that as the comet goes through the corona and it leaves behind some material, you can see that there are striations in the corona that line up with the magnetic field. So that's an actual natural solar probe. And people have modeled the trajectory of the corona and modeled the magnetic field, and its direction of the magnetic field is consistent with the striations. So that's one way to learn about the corona. So AIA is not just for studying flares and eruptions. Okay, so when sometimes we have a flare, we get the coronal mass ejection, we get the flare, but we also have material that might be relatively cool, say at 90,000 Kelvin. Not all of it escapes the gravitational well of the sun. And they can fall back. And when they impact the lower atmosphere, they can brighten up and heat up. So realities have been inspired by these observations of cold blobs, dense blobs falling back to the solar surface, and they have done radiative models. Radiative hydrodynamic models of blobs impacting a stratified atmosphere to look at how the plasma heats up. So these could be seen as templates for stellar accretion events. So what we study about the sun in terms of the aftermath of flares is also important for looking at, for example, how stars form. Okay. Another aftermath of flares, for example, is that we might get coronal rain. In this case, this wasn't necessarily coronal rain from a flare, but sometimes you see coronal condensations which appear to come out of nowhere, and they appear in a cooler channel, like in 304 in AIA, and then they drain down. Let me please move it again. That's if we pay attention to the orange blobs that form and then drain down, they seem to just drain down the loops. We get that. So these are the types of phenomena that we would like to explain for solar plasmas in general. And in times of flares, we see a combination of these that help us probe the corona and test our theories. We have the Solar Dynamics Observatory. A lot of us here know about SDO, but believe it or not, SDO was launched almost 10 years ago. So on February 11th is our 10-year launch anniversary, and it's been delivering science data at about 2 terabytes per day, every single day since 10 years. In November, we had the 200 millionth image from SDO AIA. It's a comparative order of magnitude number for HMI. And then we also have EVE that's been observing the spectra, EUV spectra. So we have this wealth of information, and we can try to study the physics. So let's go to the physics. Before that, let's look at the different channels and remind ourselves what we're seeing. So we have from HMI, the surface, showing the photosphere. We have the magnetic field measurements. We have the UV channels of AIA. Here in the 1700 angstrom continuum, we see some parts of the upper photosphere chromosphere. And then we see the 304. There are filaments that might be above polarity inversion lines. 304 is also bright, generally above active regions. In fact, 304 is quite linearly correlated with the fluxes of active regions, as reported by Ugarte et al. As we go towards 1 million Kelvin, we start to see coronal loops protruding out from the magnetic field regions, the active regions. But the corona can get hotter and hotter, and it looks different. And the hotter you go, the darker the non-magnetic regions are, or I should say, the darker the non-active regions are, and you start to only get signal towards the stronger active regions and the cores of active regions. And when we first introduced the different channels of AIA, we say that, for example, 94 channel shows 10 megakelvin plasma, and we had different temperatures for each wavelength channel. We saw this before, but that's actually a fib. If you want to understand what the channels mean, and if you want to create models of the solar corona, you can do as the Michigan people do, create an MHD model of the corona, coronal heating functions of theory, and then you have the thermodynamic distribution of the plasma, and then you can synthesize the AIA signals. And here they're comparing that, they tune the model so that quantitatively, on average, it reproduces the AIA signals. So that gives them some confidence that it does a fairly good job. And so those models get applied to other stars also. For example, for the TRAPPIST system, in order to look at the space weather around other stars, to examine exoplanet habitability. So by studying our corona, using EUV images, we're calibrating our models that we can use for other astrophysical objects. And EUV astronomy would be quite useful for looking at a range of astrophysical objects, if not for interstellar extinction. So, for example, when you have stars that go very near black holes and they get tidally disrupted, these are called tidal disruption events, then they can emit very strongly in the EUV. In fact, most of the radiation, the radiation peaks in the EUV. So if we could observe tidal disruption events in the EUV and see the megakelvin plasmas in those events, we could learn a lot. But unfortunately, EUV gets absorbed through long distances, so we don't use that. But anyway, back to the sun. Okay, so what exactly are we seeing in AIA? These are 6 different channels, not including 304. What I told you before about each channel having a particular temperature is a lie. And the reason is that within narrow band paths of each of the channels, there are a bunch of emission lines that's forming at different temperatures. And as examined by these authors here, in this 2010 paper, there are lines that form at lower temperatures or hotter temperatures in the same channel. And so when you calculate the temperature response using some assumptions with atomic databases like the Chianti package, you get curves like this. The way to read these curves is this. For example, for the 193 channel, I don't know where my cursor is. I can't find my cursor. The green line, you look at, for example, at 6.2 megakelvin, and then you read on the left side that for a given emission measure, that is the line of sight integrated electron density squared, for a given amount or unit of an emission measure, it will create so many counts in AIA. or count rates, data numbers per second. And so one particular channel will be sensitive to some temperatures and others, but generally because of the different emission lines in a particular wavelength bandpass, you have these complicated temperature response functions. So we have to live with that. So given that each channel is multithermal, of course, this is a log plot, log scale that we're seeing on the left. So it's not that bad, but still we have multithermality in the channels. But what we really want is to disentangle the multithermal nature of the channels from the possibly multithermal nature of the coronal plasma that we're seeing. And so because we assume optically thin radiation forming the counts on our detectors, we can basically set this up as a linear problem where we have the emission measure X, and folding through the temperature response functions K, we get our AIA counts. So Y is a vector for each pixel of the different count rates, and each row of K are the temperature response functions as plotted here. Okay, and then we can express this, the X is essentially the emission measure distribution as a function of temperature. And you can express the emission measure distribution as in terms of different basis functions. And so we can reformulate X in terms of some coefficients M. But anyway, so the idea is that we want to retrieve the emission measure distribution as a function of temperature using the AIA data. And we have a solution for this from the AIA team. It's a sparse inversion. And the way it works is basically we want to minimize essentially the amount of emission measure needed to explain the signal. So we're essentially wanting to minimize the total emission measure in any given pixel subject to the predicted counts being equal to the observed counts. But since there is uncertainty in the count rates, we have these inequalities. So within a given tolerance, we want to minimize the stuff that we need to assume in order to explain the predicted signal. What the sparse solution is about. And in the Chung 2015 paper, we validated this on different types of thermal models, whether it's simple log normal models or loop models on nonlinear force-free models or 3D MHD models. So we validated the method, and then if you apply it to real AIA data, then you get temperature maps of active regions that look like this. You can scan in log T space to look at the temperatures of different loops, or rather loops at different temperatures. So below 1 megakelvin, you predominantly see the fan loops at the edges. And at 10 megakelvin, if the active region is complicated enough, you might see the core loops that are the sheared field, as is indicated here for case 11158. And when you use Eve to look at certain active regions and use the different spectral lines at different temperatures, as Moran, Brooks, and Weinberger did, you can scan and look at the active region at different temperatures. This is the progression that they have here from left to right, from top to bottom. It's increasing temperature of the line. So you can see the core corona in the middle panels, but then in the bottom right, you only see some bright point and some hotter loops in the core. But you can get this progression using an emission measure inversion just from AIA alone. So this is the same active region, scanning in temperature space. And you can see that progression of going from something that looks like a sub-megakelvin stuff in the active region to the fan loops, to the core, and then to the bright compact loop at the top around 10 megakelvin. Okay, so it seems like you can use AIA to find the temperature structure of active regions. We're talking about this because we eventually want to actually apply this to flares, because AIA is observing the sun all the time, and other instruments might have limited fields of view. So we want to study a lot of flares. We want to use AIA as much as we can. But there's another cross-validation exercise that we could do. And that is that often we also study flares using X-rays. And these are the temperature response functions for Hinode XRT, distinctly different than the ones for AIA. And what we did was, this was not in the paper, but what we did was to use AIA data only and invert for the DEM solutions, and then multiply that by the Hinode XRT temperature response functions to synthesize the XRT signal. So the middle column shows the synthesized XRT images. The left columns show the actual XRT images. This is for the titanium poly filter and the aluminum poly filter for the top and bottom rows. And then we can compare using a 2D histogram the actual ground truth with the predicted. And overall, over 3.5 orders of magnitude, it matches pretty well. It fits about diagonal, which is when it's perfect. But there is a bit of an offset. And this offset of about 30%, one can possibly prescribe to the uncertainties in the absolute calibrations of the three instruments. But when you look at the morphology of the loops, it seems that the predicted XRT images are consistent with the actual XRT images. And so this gives us further confidence that you can actually look at some structures that you would otherwise be interested in studying with X-ray images, but using AIA EUV images. Another lesson is that just because there's stuff that you see in X-ray images doesn't necessarily mean that this plasma is at hotter temperatures than what you usually associate with loops in EUV images. It just depends on the DEM. Because in the end, when you look at the temperature response functions for XRT, there is still sensitivity to temperatures where AIA is designed to operate. Okay, so now let's really go to flares. So let's apply our DEM to a limb flare, which has been well studied. And people have looked at the DEMs also for this flare, but we analyze it a slightly different way using our method here. So we solve for the DEM distribution, and let's look at the emission measure weighted log T. That's shown in the color here. And so this is a limb flare that will eventually have an eruption going towards the right. So the color shows the emission measure weighted log T. And then along the horizontal dashed line, we plot in the red curve what that emission measure weighted log T is along the dashed line. And then on the black curve, we're plotting what is the total emission measure. So along the dashed line going vertically up, the solar atmosphere, we have loops that are generally the corona is about log T of 6.6, and the total emission measure has a fall off with height, that has a scale height that is consistent with this log T, okay? So it's reasonable. It's a fairly steady corona. Okay, so when the flare begins, you start to see enhancements in both the emission measure weighted log T in the red curve, as well as in the total emission measure. That's the beginning of. And as the flare progresses, these humps increase in both extent and in absolute magnitude. And so because we are plotting these curves on a log scale, the height of the bumps corresponds to the relative difference. So the relative increase. The relative increase in the temperature is higher than the relative increase in the emission measure. Just keep that in mind. And apart from the big bumps that's on the left side, you also get these bumps towards the right side. So those are two outflows from presumably those are the reconnection outflows of the flare. One towards the sun to the left, and one away from the sun. And then as the flare progresses, you get a pileup of the loops, and the enhancement in the emission measure weighted log T starts to not be coincident with the emission itself, the emission measure itself. And then actually the peak of the emission measure weighted log T in the red curve starts to migrate higher and higher up. And if you were to look at the flare at this stage in 94, this would be the fuzzy, the blob up there would be the fuzzy 94 signal that you typically see in limb flares. Okay, so this is the sort of evolution that AIA is showing us in the thermal distribution of the plasma in this flare. We can look at it again. So initial, some enhancements, ensuing flare, and then the hot plasma migrates, whereas you get a very, very strong enhancement of the total emission measure just near the top of those loops that we see in the EUV. We can interrogate the data in a different way. Again, the color is the emission measure weighted log T. But we can also plot contours of the total emission measure. And so what we find is that there is this enhancement in this cusp, at the top of the cusp, an enhancement in the total emission measure, but we also see an enhancement of the total emission measure at the foot points. So these are disjoint contours, whereas the temperature is more uniform. It extends from the cusp through the foot points. Okay, so one can imagine that the emission measure enhancement at the top is due to downward mass pumping from the reconnection outflow, and that's the enhancement at the foot points would be signs of the chromospheric evaporation. This is how the movie looks. And then the foot point enhancements start to lift towards the top of the cusp. And at some point, you get such a strong enhancement in the emission measure when it seems like maybe the evaporation flows have reached the top. We can compare it with MHD simulations. In this case, Shiotta et al. Carried out 2.5D MHD simulations of a pre-existing flux rod which erupts due to some flux destabilization due to flux emergence. And it's an extension of the Chen and Shibata paper, except that they included field-aligned thermal conduction in this model. And so when the eruption begins, when the reconnection begins through the current sheets and you have these reconnection outflows, the shortening of the field lines creates density enhancements and temperature enhancements. So the left column shows the density enhancements, the right column shows the temperature enhancements. And the temperature enhancements stronger than the density enhancements. The magnitude of the enhancements is basically similar to what we saw in the data. And the enhancements in the outflow away from the sun is weaker than the enhancements in the outflow towards the sun. In that sense, it's also consistent. This type of work has been extended by Takasawa et al. In 2015. They carried out these simulations of chromospheric evaporation following flare reconnection. And so they begin by having these anti-parallel loops that are threading the vertical direction, and they reconnect from the top of the simulation domain. And this is a stratified layer. And when there are the loops that retract from the reconnection outflow, you get evaporation flows that's the strength of which depends on how much thermal conduction is built into the system. So the top panel shows essentially the log T. The middle row shows the density. The bottom shows the vertical velocity. And from left to right, we have no thermal conduction to increasingly higher thermal conduction. Let's look at the movies again. Okay, so when you have higher thermal conduction, the enhancement in the blob at the top of the cusp is stronger. Okay, when there's no thermal conduction, it is weaker. And you can extend this away because when there is thermal conduction, when you're compressing the plasma, even though the temperature, even though the density is increasing, the temperature doesn't, and the pressure doesn't increase so much because it can conduct away. And so it can be more compressible. That's why you have the higher density when there is stronger thermal conduction. Okay, and then when you have thermal conduction, as we would expect, the energy gets conducted down to the base of the corona. It gets dumped into the chromosphere, and with strong conduction, there's a stronger dumping of the flux of the energy there, and so you get stronger chromospheric evaporation flows. Okay, so that's sort of those are the sort of physics that one can try to learn from using AIA DMs on limb flares. There are other things that we could learn with SDO. It turns out that for some very strong flares, you can actually see the flare in HMI data. And it's relevant not just for the solar flares, but for stellar super flares, because in Kepler data, it's been reported mainly by the group in Kyoto that there are these very, very strong flares that are orders of magnitude stronger, larger than solar flares. And typically, in order to estimate the energies of the Kepler super flares, it is assumed that there is plasma radiating at about 10,000 Kelvin, blackbody radiation, at the base of the flare loops. Okay, but it turns out that you can even see contributions to flares in the visible in the loop tops when you have strong flares, as demonstrated by these HMI observations of this limb flare, and the brightening in the visible is not just due to Thomson's scattering. There's a significant contribution actually due to the Paschen continuum, as revealed by these authors here. I don't know how to pronounce Jesic, Heinzel and Kleitz, and also see Heinzel et al. So there is another emission mechanism that could explain the brightness, and you might not have to attribute all the flaring emission that Kepler sees just to plasma at the base. You might have to consider the loops also, and you might have to consider that it's not a blackbody radiation, but you have to consider the emission process in detail. So Heinzel and Shibata suggested that the observed white light flux might be due to a combination of a ribbon and loop radiation, and it could be loop dominated during the gradual phase of super flares. And this is important. So given that they have made this suggestion, it might be worth going back and looking at whether using this interpretation, how different the estimates of the energies of super flares would be. Now, I haven't done that. I'm just suggesting that this is something that ought to be done. Okay, so more recently, I've been involved in a large collaboration funded by the Heliophysics Grand Challenges Research Program to model flares in 3D using radiative image simulations. And the idea is to be able to do these radiative image simulations and then observe these simulations and see whether what we learn from our synthetic observables actually it corresponds to what we actually have in the ground truth in the simulation. And also, of course, we want to see whether these simulations produce observables that look anything like real observations at all. So we were inspired by active region 12017. It was the first X-flare observed by IRIS, and at that time it was called the best observed X-flare. And actually, this region had a bunch of flares, also 3 M-class flares and 2 C class flares. But let's look at this movie of the emission distribution. So the different panels, the color panels show the amount of emission measure in different temperature bins. The top left shows emission measure below 1 megakelvin. The ones on the right show hotter plasma up to 10 megakelvin. And then we have the line of sight magnetogram in the bottom right. Overlaid on top of that is just the hotter plasma, flare plasma. So we can play this movie and see where the hot plasma is relative to the magnetogram. And you see that generally the hot stuff appears above an emerging flux region. So there was a pre-existing sunspot, and north of this pre-existing negative polarity sunspot, there was a parasitic dipole emerging, and that seems is driving a series of flares in 12017. Again. Right. So we were inspired to model this event because we had limited computational resources, and the fact that this parasitic dipole is emerging next to the sunspot means that it has to interact with the sunspot canopy field pretty low down, so we could be confident that we can capture the interaction in our limited computational domain. And also that it gives a series of flares means that there is generally enough Poynting flux being generated, and we could have a reasonable chance that we might be able to simulate a flare like this. So this was not a data-driven simulation we did, but we were inspired by the geometries of this active region. Okay, so the MURAM code has been used to simulate different photospheric features for many years, and this was, for example, a sunspot simulation carried out by Matthias Rempel. And these are synthesized granulation patterns around the sunspot. What we did was we took this model, he extended this model so that we can model the corona. And we also included chromospheric losses from the Bifrost team. And basically, we had a pre-existing pair of spots, and we emerged a parasitic polarity.
Mark,
Yes.
5 minutes.
Yep. No problem. And then we emerge a parasitic dipole just to the negative polarity spots in this model. And so it puts up energy, and then then it flares. Okay. When we synthesize the ghost X-ray light curves from this simulation, as we see on the plot on the left, there is this fast rise and a gradual decay in the ghost light curves. And when you look at the simulation like that, then it corresponds to a C4 flare. And when you look at the simulation itself, during this flare, over about 5 minutes, about 5 by 10 to the 30 ergs lost from the magnetic energy. Now, this one flare doesn't lose all the free magnetic energy. That's not possible, because if you really want to get to the lowest energy state, you would have to untangle all the braiding in the field to the lowest energy state, and generally it's impossible, given that the magnetic field builds up the twist and the magnetic helicity through some history through the photospheric motions. So it's not unreasonable that it doesn't get rid of all the energy in one go. This I will summarize this only to say that the energy release occurs. Okay, so the energy storage is in the form of a flux web that gets created above the polarity inversion line of the parasitic polarity. But there is a bootstrapping field above that flux web. But eventually, this flux web can be destabilized because the bootstrapping field has been eroded, and through a series of magnetic reconnections through tangential discontinuities, it can open up and release the energy, and eventually relax back to give flare loops. One has to just study that plot in detail, and I don't have time right now. These are the synthetic images in AIA from the simulated flare. You mentioned the simulation has periodic side boundary conditions. But because the parasitic polarity is emerging right next to the spot, the interesting part happens where it's not that much affected by the periodic boundary conditions. Anyway, so you see also ribbons in the simulated observables. We can look at the Doppler, the emission measure rate Doppler speed at the foot points during the simulation. So those 3 curves at the bottom panel are sampled at foot points shown above. It's very dynamic. But what we find is that generally above 1 or 2 megakelvin, the speeds are upflows, whereas below 1 or 2 megakelvin, it is downflows. So it's consistent with work that has been reported from observations, for example, by Delzana and by Milligan, that there is this trend from downflows to upflows with temperature. You can also synthesize the X-ray spectrum from the simulation. And synthesize what RESI might see in terms of flux contours for different energy ranges, like for example above 25 keV, shown in the red contours, or between 6 and 12 keV, shown as the blue contours. And what we find is that despite not having any particle physics in this simulation, non-thermal particle physics, just by synthesizing the thermal bremsstrahlung, we can get, during the flare, a spectrum that looks like a power law. But this is purely due to the multi-thermal nature of the plasma in the simulation. When you look at the emission measure distribution in the top panel, the the red dotted line, you see that there is plasma that extends all the way to the above 100 megakelvin, albeit very little of it. But there is this extended tail, so it's extremely multi-thermal. So there's no particular reason why we should think of this system as a monothermal region. And when we just synthesize the spectrum, we get something that looks like a power law. So this is not to say that non-thermal particles are not important for flares. For certain diagnostics, for sure, they are important. For the total energetics, it's not clear from this that they are that important. Some of it can be explained by just multi-thermal plasmas. And especially for the X-ray spectrum, at least for the coronal source, at least when we interpret the data from the sun, we should accommodate for the multi-thermal nature while we think that non-thermal particles might be important. At least we should give that possibility. Okay, so we can also do data-driven simulations by using the magnetograms and extracting electric fields. And then you can use electric fields from the photosphere to drive a data-driven simulation. This is not full MHD, this is magnetic friction. I won't have time to talk much about this. I won't show this either, but by doing this data-driven simulation, we actually find that for 11158, we can create a flux itself consistently through the photospheric motions, twisting up the field, emerging field, and then have two polarities colliding. And above this colliding polarity inversion line, you get this flux and arcade, and they can reconnect and destabilize. So, but this is not full MHD. So the holy grail, I think, is to be able to do these types of calculations using full MHD, and people are starting to do that, but not so far computing directly the synthetic observables, whereas they're just tracing field lines and comparing with loops. But we want to be able to do that too. So, in summary, there's a bunch of astrophysical processes that we study from the sun that are useful for flares, but for other astrophysical objects also. And a lot of this information is encoded at EUV wavelengths. But AIA has excellent temperature coverage. And we can certainly benefit from DKIS. I didn't talk about DKIS, but there's a lot of things we can do. For example, with the high visual quality of DKIS data, we can do data-driven simulations of the detailed structures. White light flares, I would say, might not be completely understood. And especially for super flares, maybe we have to look at the loop contribution. MHD models, after they've been validated against the sun, can be used to look at exoplanet habitability. And in a data-inspired flare simulation, we can produce observables that are reminiscent of observed flares, but we really want to be able to do data-driven simulations. And then the SDL dataset is a treasure trove of physics-based and machine learning models. We can start using the data to learn something about flares in a statistical way. For example, for flare prediction, like a Monica Brobra et al. Have done, and other applications, including the flare prediction, are I think described in the e-book. So I encourage you to look at that too. So with that, I yield my time.
Okay, thank you very much, Mark. Now we are open for questions and comments. So if you have them, Hugh, go ahead.
Okay, I've got three. So, hello, am I connected?
Yeah, go ahead.
Hugh Hudson, yeah. Hi, thanks, Mark. That's really great. All kinds of neat stuff, and these, not just the DEM stuff, but anyway, you talked about so many topics. But the first question I have is about your interest in the reconnection outflow as a source of mass for these loops in these limb flares. The reconnection entrains mass from the corona, right? And so the amount of mass that you get has to depend upon what you assume the coronal density external to the flaring structure is. And I've always thought that it would be very small because for two reasons. First of all, the corona, especially the open field corona, has a very low density. And secondly, even if it's closed field and if it opens up, then there will be a solar wind flow immediately and large. And so the reconnection mass may not be very great. You want to comment on that?
Yeah, so I didn't mean to say that the mass that was in the corona due to the reconnection outflow and the compression by the shortening field lines causes the large enhancements in the EUV and the X-rays. That has to come. That huge increase has to come from material lower down. From the chromospheric evaporation. All I meant to say from like this slide is that even though it's not that big, it's detectable, this compression, and you can compare it with physics models like the Takasawa model, or even earlier the Yokoyama model, Yokoyama and Shibata model of a flare reconnection. They have this blob. Actually, I think the technical term they used was blob. There's some enhancements at the loop top in the reconnection outflow. So it's detectable.
Well, I'd quibble about the detectability because people are always optimistically looking for these blobs, but typically in the past anyway, people have looked in the plane of the sky and not considered the 3D perspective, which you can do now.
Right, you can do that. But even if you're lucky enough, in this case, you're looking through sort of perpendicularly or down the barrel, not down the barrel, but it's just across the arcade. You get this enhancement, and this enhancement occurs before the chromospheric has time to reach the loop top. So most likely
within 40 seconds.
Well, I mean, here you already see it, like here. So yeah, within like 20 seconds.
Okay.
Okay. Yep. And so, so even though there is an enhancement in the emission measure, it really the enhancement really grows once the evaporation flows have filled the loops.
Right.
Yes.
Okay. Well, second question. May I go ahead, Gregory, with my second?
Sure, go ahead.
Okay. Well, the second question has to do with the interesting suggestion that the Kepler flares might have some. I think of it kind of as photosphere appearing in the corona, so you get a bigger flare, a bigger star, as a source of white light, as opposed to just sort of optically thin emission from something. And that depends upon the density there, of course. And as Heinzel has pointed out, if you have a very high density, the extreme that we observe in solar flares, you can get direct emission from these loops. But normally what you see is scattered light. And that was shown by Saint-Hilaire as one of the early papers on these things and finding the polarization signature. So I think, anyway, there's going to be inescapably a lot of scattered light. So the question for you is, what happens to flares, to Kepler flares on the disk? Would they appear as being bright or dark? And how would that affect the statistics of the flares that you see on Kepler, I wonder?
Right. So I haven't done the calculation myself. I really do not know whether this is a 1% effect, 10% effect, or order of magnitude effect. So and since I'm not an expert at this, I'm just waiting for someone to do it. This is just me saying that someone should do it properly.
Me too. I think it's really an interesting idea, but I think we need somebody smart to work on it. So further, anyway. Okay, so question number 3, if that's okay.
Yeah.
Just a comment, maybe, it is that you said that the remnant twist in the corona following this big flare, which leaves a non-potential structure there, for example, would be due to twists, flows in the photosphere. But I just like to point out that the timescale of a flare is so short that these flows don't act, and what you have is the curl of B in the foot points, which is a current. So the current is not interrupted by the flare. It's still there, and it just changes its geometry. So you don't need to appeal to anything further than just inductive storage for this kind of a thing, I don't think.
Yeah, so that's also not what I was meaning to say. So what I meant to say was that in the build-up to flares, you have this, for example, flux emergence or shearing, which could be or instigated by flux emergence. So and it happens over hours, or minutes, hours, or even like days. And there are these patterns that have a history, and it's winding up the field. It's braiding the field in a complicated way. So for every enclosed, every magnetic volume that you can come up with, you can calculate a relative helicity. For example, following the Malin-Nashim and Loncker method, and that has to be preserved if you want to invoke the minimum energy, preserving that. So all these topological, there are all these topological invariants, and not just a single topological invariant, not a single relative helicity that is relevant for the whole system. And if you want to be able to go to the minimum energy state, you would have to untangle all these, and there's a reason why you should be able to do it in just one go. That's what I was trying to say.
Yeah, I think what I'm trying to say is that there's more than topology here. It's also physics, all right? And so if you have currents in the corona, you have got twist, and you have non-potential energy. That's the
Mark,
physics.
When you think about reconnection of two, let's say, current field lines, if you think you cut them and reconnect, then you can have very conflicting electric currents. So you expect a whole bunch of electric current redistribution processes to end up to something reasonable.
Yeah. So let's say you have one current sheet. You have some tangential discontinuity, and then that allows to break the topology so that when the field lines retract after coming out of that current sheet, you lose energy, and then it goes into a new state. But there's no particular reason why that new state would be necessarily so close to the potential state, because you might have to go through a bunch of reconnections in order to do that. There is no guarantee that there is a simple pathway, and one eruption is one pathway, but you might need several.
So Mark, I don't think these current sheet currents are the energy source. The currents that provide the energy for the corona are the photospheric currents, the vertical currents out of the photosphere. So you can do all kinds of reconnection if you want to. That's good, but you still have to maintain those currents because the interior of the sun has a very slow time scale, and it just is going to be there.
Yeah. So the currents. So it's hard for me to think about the evolution of currents. Because if you want to think about how currents evolve in a 3D volume over time, it's not a differential equation. It's an integral differential equation, and I just cannot wrap my head around it. So the easiest way for me to understand the system is to think about the magnetic field evolving, and then the current just follows as the curl, at least in my simple MHD world. And in that world, the energy decrease of the magnetic field enabled by magnetic reconnection is predominantly, as demonstrated by Dana and some other people, when the field line is retracting after going through the current sheet. That's the Lorentz force that is releasing the magnetic energy.
Yeah, that's the flare implosion.
As you are well aware.
Okay, so any other questions or comments? Mark, I did have a very short question about comparison between synthetic AIA maps and XRT maps. I wonder, could any assumption about abundances affect your comparison? And in particular, do you have strong free component contribution to XRT emission stuff? So comment on that.
So let's see, the temperature response functions I use.
This correlation, yeah.
The temperature response functions for XRT I used here is the same that was used for calculating the AIA temperature response functions. But yeah, it includes the free emission, of course.
Yeah, it includes free and includes some assumption about abundances.
Yes.
Most likely standard coronal or something like that.
Yes, but I think we're using the same one for AIA and for XRT, and now the question is whether the dependence of the temperature response functions on the abundances is different between the two instruments. Is that what you're asking?
Yep.
Right. There could be that, but I spent sort of a few days talking with people like Kathy Rees and Mark Webber, and we couldn't pin down the difference as due possibly to that. Really, we think the AIA intercalibration, I mean, the absolute calibration is, the uncertainty is like 25%, and then XRT says it's like of order 10%. And then, you know, the DEM inversion, it visually looks good, but it might not be perfect. But I think that yeah, given that it is the morphology looks so close, then it could possibly be abundances or just the absolute calibration. It's hard to disentangle for me, but that's a good suggestion.
Okay, let's talk later offline sometime about that. I'm interested in this question. Okay, any other questions or comments, last minute stuff? No, everyone is muted, so thank you very much, Mark. Yeah, thank you for your talk. Yeah,
Thank you for that. Okay, thanks, Gregory.